start. And welcome everybody. My name is Esfandyar Kuhi and I'm Simulation Product Manager at Intercad. Today's webinar is about design study and design optimization option in SolidWorks. This is the fourth session of design validation webinars conducted by Intercad. We're aiming to assist designer and engineer to utilize their simulation needs. And also the upcoming events as shown is just one event left. On 20th of September we have steady state versus transient thermal study in SolidWorks. If you are interested on the topic and you haven't registered, please send me an email by end of the session and I would provide the registration link for you. We are also organizing series of seminars to present the capability of the software in various applications. It is a very great opportunity to have a face-to-face meeting with our valuable prospects and customers, and we can understand their specific simulation need. The first seminar is conducted by Intercad on 26th of September in Melbourne, where the registration link will be sent to everybody in a few weeks. Again, if you are interested on this, please send me an email and I can provide the registration link for you as well. All right, let's start our work today. We simply splitting this session in two main categories. First, we going through a design study case where we're defining a few things at the beginning, such as design variables and output parameters. Then we introduce a case study on a vehicle suspension, where in this case study we introduce how we can do a variation on loading input and also how we can select any geometrical dimension as an input and specify the range of parameter. In the second part, we're going for design optimization, where we have same definition and we introducing one more parameter here, which is the goal of optimization. We will have more in detail description about the variables, goals, constraints, and then we have a case study of how we can optimize a press frame mass while we limiting a few parameters such as maximum stress, deformation, and frequency. Okay, let's start with the design study definition. Design study is performing several studies for different input data, where we call them design variables, and then review the result as a function of design variables. These inputs could be loads, where we can varying their magnitudes and directions. Could be geometrical parameters, such as dimension or the features suppressed. Or it could be material property, like a constant material properties or their property curve, where these inputs will be processed in a design exploration, and as an output we can review how the stress max mean in a different scenarios or displacement or deformation could be varied while these magnitudes and list of inputs are changed. In this case, we will have this option fully explained through a design scenario case study, where in the first, let's say, case scenario, we will have a vehicle suspension system with all the components as you can see in the figure, while the hub section is under vertical and horizontal or lateral, let's say, loading. But we would like to see if we have a range of load, how the response of this structure will vary. We will explore stationary and loaded, where the vertical loading, the lateral loading would be 0, and vertical loading would be 225 Newton. or moving at the constant acceleration on a smooth road, where the magnitudes of load will be changed to 60 and 185 Newton, or moving on a bumpy road, where these magnitudes are 72 and 385 Newton, and the last scenario, where it's moving at a constant speed on a banking road, where fourth scenario, the loadings are 115 Newton and 900 Newtons. Okay, let's go to the case study and bring the model. Here is the model. And let me bring it to screen. Okay. Here is the model. As you can see, we have a hub section. Attached to it is upper arm and lower arm. And we have the other section as a choking section. So choking section, hub, upper arm, and lower arm. What we have to do is simply, before any design case study, we have to create a static case, first of all, where I have created this here, and let's review what is there. The first item we have to review is all the components material properties. As you can see, alloy is still being assigned to all of them, all these components. Next is to create the connections. We have a list of connections. As you can see, there are pin groups where we simply putting here. We have 8 pin, as I'm showing you. And the last thing is the spring connection, where it's been assigned within suspension system. The whole components are considered to be bounded with a global contact set, and then we have to define the fixture, which is a hinge fixture. If I edit definition, you can see these 4 faces on an upper and lower arm is been assigned to have a hinge fixture type. Okay, the last step is where we define the loading. So like any other static case, right click, force, and now we can apply the force at any direction we want. This is being created here, and you can see on the face of the hub, normal to front direction, and we assign 2 values for lateral and normal direction. Now, from this point, we are starting design optimization, exploration study. These values are absolute values. However, we can set them as a parameter, and later on we can specify a range of variation. How we can do that? Whatever initial value you put there, if you just expand this, there is an option to link the value. Click on this, will give you a new communication window where it's saying select a parameter or edit and define. Simply what we do, we can put the magnitude of lateral and vertical load to be set as a parameter. That is a parameter, not absolute value. How we do that? This has been predefined. However, I can put edit and define. Simply you're going to a new row, type in anything you like. Then in a category section, if this is from model dimension, is any geometrical parameter, then you can select this, global variable, simulation data, or material data. So basically it's a simulation data, and simply you put in your initial value as you like. Clicking OK, then it will assign this value, initial value, but it will consider it as a range of parameter to be varied later on. If you have predefined this, then you can simply link your value anytime to the list of parameters you have specified. For the first item, we have to create the new value, edit, define, and make the first one as vertical with value of 225 and the second one with the value of 0 as it was on our case study 1. Click OK and simply link this to vertical. Click OK. You can see that is been gray and it's not, sorry, I have to link to lateral, sorry. And second is link value to vertical and click OK. When I've done this, if the parameter is linked, then we have a gray field and it's not available for, let's say, changing. Now the parameter is being set and the study is basically created. Now what we can do is simply we can go and click OK in this case. Now we have created our case where the loadings are simply linked to the values, and we have a new icon appearing here which says parameter. You can always edit and define and list what you have here. Alright, you can see these two values are linked, initial values are here, and the units is simply Newton. Alright, next would be meshing. We are going to accept the default setting and click OK. When the model is being meshed, you can always review, and if any modification you like, you can put it there. And now the study is ready to run. It is very important to always remember we have a base study and then we explore the design option or optimize the design option. So the basis is always what you're creating. We have an alert or warning of saying we have large displacement, so we're clicking no and accept whatever here. Now you can see what we have at the moment is telling us we have around 158,963 Newton per meter square or Pascal as a stress value, and displacement is showing us 6.52 millimeter. Okay, now we are exploring our first option. Now how we can define the range of variation. That could be done if you go to evaluate and you have the design study option here. Expanding this design study and you're creating a new one. Now we are in a new interface where you can see it is design study, and in this section you have range of parameters to be defined. First is your variable view, second is your table view, and third would be result view. For those who has the simulation professional license, this option as optimization is getting active, otherwise it is not active. Because we are doing design study, we are just unticking this. Alright, now what we need to do first, we say there would be some variables that we would like to make a range of variation on them and do the design study. Where we can do this is simply here, variables. What are the variables? They are the one which we added as a parameter before. If you just forget to add them as a parameter, you can always do this here. If you put on add parameter, you can create them here as well. So there is no need to pre-assign. Because we have created before, then we simply select them. First lateral. We can specify them to vary in a range with the step size, scred value, or a range, where in our case we are simply interested on the range of them. Which is here. Why it's just giving me this? All right, 1 minute, guys. Sorry. Range. Secret values. Okay, secret values, and here. So what we have to put here, first is 0, second is 60, next is 72, and next is 115. That is the first range of the lateral load. Corresponding to this is the vertical load we have. Again, it should be a range starting from 225, 185, 385, and 900 newtons. So simply, we said the first set is 0 and 225, then 685, then 72, 385, and the last case 115, 900. So we said what is the parameter first, then how the parameter change as a set of variables. After this point, what we have to do is simply putting some sensor. Sensor means what sort of property we are interested to measure. Is it stress, strain, displacement, anything? And we simply can monitor them, and after the design study is being completed, then we can simply review them. This sensor could be defined as evaluate, sensor, click, and you get a new communication box. In a sensor type, you can choose any property from simulation data, mass properties, dimensions, interference detection, measurement, and proximity, where we are interested in simulation data. For the data quantity that sensor will collect for us, you can select stress, strain, displacement, frequency, and etc. as you can see. In a stress category, one misses principal, normal, or shear in any direction. And for the properties of this sensor, first you can say what is the unit and what this sensor is going to measure in a stress form. Is it the maximum stress over the whole model? So it is model max. If it is minimum value over the whole model, is minimum model, and then model average. Or you can simply select any entities to measure or let's say record its maximum, minimum, or average. Selecting this item, you can go anywhere on any point or any line or any surface, and simply saying I would like to have a measurement device where this measurement device is located here, and it's measuring stress value and stress value in one misses form with this and the maximum or minimum or the average. So we simply putting our instrument for measuring here. We have, when you're clicking OK, you will create, if you go to the model, you can see in a Design Manager tree, these are the sensor you have defined here. Let's review them. Edit sensor, and from simulation data, we put stress, maximum over the whole model. That is the first sensor. Second is same for displacement, simulation data, displacement, and resultant. In millimeter, maximum over the model, and all the steps. Then we had created a sensor on a vertex, so selected entirety, and maximum value of stress one misses, at that point. And the last one is the displacement on the same vertex. So maximum displacement, maximum stress at the point, and same for the whole model is what we want to measure and review later on. So since we created that sensors and we put our measurement devices on our model, then we have to come back to the variable view and say what is our constraint. And basically these are the sensors we actually defined there. You can always add sensor in this communication box, not going to evaluate section. And if you're happy with whatever you define there, simply select them and you ask for monitoring. This monitor and this sensor is getting its initial value based on the previous static study we run, which is multiple loads study we have created here. We can add more sensor, displacement for monitoring, and we simply selecting the static study here. Next one, stress 2 for monitoring and based on our initial static study. And the last one is displacement on the node, which is monitoring, and it is based on multiple load scenario. Now we have fully defined our design study option. So as a review, we simply created an static case first here. We simply set up our model, material, connection, fixture, loading, meshing, and everything. We assigned some of our area of interest, such as load, vertical, and lateral, as a design parameter, and we specified their initial value. We ran the static case. We created a design study, let's say, case, and then we're selecting our variables and the range. We're selecting our variables and the range. We said what sort of properties we want to measure and monitor. So stress, strain, displacement, and etc., where it's based on our previous static study. Then we can have a table review about what sort of scenario we have created here. The first scenario is telling us, if I show you here, the first scenario is telling us lateral load is 0, vertical load is 225. Scenario 2, it is 60, 185. Scenario 3, it is 72, 385, and the last scenario is here, 115 and 900. So we are ready to run our case study, and then take it from there. We have, before we're running, we have the option of setting, do we need a high quality design study option? If we select fast result, some of this scenario will not be solved randomly, but what happening is the software is going to evaluate the values of that scenario from one before and one after. It will showing us where the result is going to, let's say, put there in SolidWorks document folder, or you can specify it yourself. Click OK, and you will accept. Now we are ready to run this case scenario. Clicking on run, and you can see it is processing the scenario 1 out of 5, where result view are simply going to update very soon. So the software will get the initial static study result and simply coming with the list as one scenario is being solved. Currently, vertical load is 225. Oh, the model is now, okay. Currently, lateral load is 0, vertical load is 225. Initial value was the same thing, and scenario 1 is being built on the same case. Next, as scenario 2 is being resolved, and we have the load of 60 and 185 here. You can review that stress value on maximum stress value over the whole model was 158.963, where in the second case it's been reduced to 139.567. In scenario 3, it's been increased to 282. Same other sensors you have defined is all getting solved here, and you have monitored them. So stress 1, displacement 1, stress 2, displacement 2. So you can have a review of your result at this table stage. You can save this as a CSV file, or you can load any study from your previous study as a CSV file as well. However, if you simply select your first scenario and going here, you can have a visualization as well. So stress value over the whole model in scenario 1, where the maximum is being listed, but you can go for second scenario and look how the stress is changed. So you can see from 159 max is coming to 139 maximum. Simply selecting any scenario, you will review the result. Where basically in scenario number 4, as you can see, you have passed the yielding point and the part is going to fail at some specific region where it's been highlighted here as well. Alright, so that is simply set up a design study case, and we can review any scenario we would like as variation of the load. Same option we have if you would like to select any geometrical parameters in our design study. How we can do that? We can simply create a new design study, and this time as a variable we can simply select arm thickness. Before that, we have to specify this parameter, where I have did again, and this time arm thickness is the model dimension. You can always go and view your annotation here. Simply go to your parameter, say for example arm, model dimension, and select it. That is all been what you're doing, and simply 3 mm as the initial value in arm thickness is there. Simply after this, what you can do, you can say arm thickness and variable is changing with the range with the step, where minimum we consider 1.5, maximum to be 8, and step size of 0.5 millimeter. Again, we are interested on reviewing the stress displacement result on the whole model and in some specific, let's say, area. Then clicking on run, and here is the result we get. Scenario 1, we can view the stress value. Scenario 2, where this thickness is 2 mm and the stress value maximum is, as you can show here. One by one, you can review your result and see if the thickness is changing from 1.5 to 8. You can review your maximum stress, maximum displacement at any place you like. Also, you have the option of defining a design story graph on your design variable or on your constraints. Simply select them and clicking OK, where we have defined one, simply showing us the maximum stress value, for example, on the whole model was starting from 1800 megapascal on set 1 and decreased on set 12. We have a bit of increase on set 13 and then set 14. Simply by this, we can see that how our variables could change over the range of the design parameters. Okay? So simply what we had up to this point is showing to first create a study, specify some parameter which could be loading or could be geometrical factors as a parameter, then specify a range of these parameters in our design study, and then say what is important as an output to trace, could be stress, displacement, or etc., and simply run the case study. This is what we call design optimization. Design study exploration, where different scenarios, different things you may consider will come as quick as possible as a list of file or detailed graphical views. However, there would be a question here. I said, all right, I know all of these, but I can't really decide which one is the optimum one. Is there any way that the software is going through the list of variables I have provided and list of, let's say, limitation I would put there and decide which one is optimized? The answer would be yes. We have this option available in our simulation professional license, where let's review the facts about this. And let me get back to the screen, where this is called design optimization. All right, so let's bring this. Yeah. The second option is about design optimization, where we're trying to find the best design by changing geometry. The main difference between design optimization and design exploration is we have to define a goal, an objective, where very common one in a static analysis is to minimize the material. We also have design variables where it could be loading, any dimensions. In a case of feature, could be their sketch dimensions or the extrusion or cut extrusion or any other parameters we basically can find in SolidWorks. And the constraint here is not just for monitoring. We can have or set a limiting conditions on this constraint. For instance, we would like to have the maximum stress for some certain value and not exceed that. You will tell the software, this is what you're wearing, this is the limitation you have, and the goal is to reduce the mass and let me know what is the optimum. One extra thing I would like to add is, like what you had in design exploring, we have to create an static case or frequency case or buckling case or thermal case beforehand, and then use that initial result to create your design optimization case. Let's explore more. First is about goals. The goals define the goals of the optimization process. For example, minimizing volume or mass. That could be defined over the parts or, let's say, assemblies, where we're trying to get the performance or the specification for our design with the minimum volume or mass. In buckling analysis, could be maximizing the buckling load factor, or in, let's say, frequency analysis, could be maximize or minimize the resonance frequency. For the variable set, as we explored before, these are the dimensions or loading factors that you will select, but it should be very, very carefully select that there is no contradict with the other dimensions you have. For the constraints, this is the place we're putting our limitation, not just for monitoring, this time for limiting and telling what is my design criteria. For instance, for static studies, nodal or elemental stress, strain or displacement could be a constraint. For buckling studies could be first through the 10th buckling load factors, and for the frequency analysis would be first to the 10th resonant frequencies, and for thermal studies could be temperature, temperature gradients, or heat flux. All right, with this overview, now let's focus on our case study for today. In design optimization, we're trying to optimize the mass of press frame, as you can see in this picture. The initial dimensions, as you can see, we have height of side plate initially at 100 millimeter, but we specifying this as a variable to vary between 50 and 100 millimeter. Length of the back plate 375 millimeter initially, but we setting the range of 150 to 350 millimeters. And cut of the legs here, where it's varying from 100 to 250. So these are the variables, and it's geometrical variables to be varied, but we have our limitation. We specifying, or we telling the software that maximum stress while you varying these parameters should not exceed 100 megapascal. Maximum deformation should be less than 1 millimeter, and the smallest natural frequency should be more than 80 hertz. With all this condition, we understand that we have to create an initial static case for our initial model and initial frequency case for our initial model. Then we define a design study and we tick on optimize, we specifying the variable, goals and constraint, and then we can review the result. All right, let's go to the case study. Here is our model, the press frame, where initial values, as you can see in the model, we have 375, 100, and 100 on here. As we said, the initial step is to create an static case, reviewing the material properties. We have plain carbon steel applied to all components. Components are in global bounded contact. We have a fixture on the plates, 4 fixture, fully fixed, and we have a normal force acting here with the magnitude of 22,250 Newton. First, what we need is simply create the mesh with the default values, click OK, and simply run the study. Initial study is simply telling us the magnitude of one misses stress maximum is 62, is less than 100, what we actually, let's say, considered. And also the displacement value is 0.3 millimeter, less than 1 millimeter. And everything from performance prospect is maintaining here. But the question is it optimized? The mass of the system is optimized? Is it, it could be less, with varying the dimension, could we get less mass on the actual system? Also, we said we have to perform a frequency analysis. So simply creating a frequency analysis by saying new study and then frequency, click OK. I have created, simply copying all the conditions I have, create the mesh, and then asking for running the result, and then review the other condition, which is the first natural let's say, frequency on the model. The first natural frequency is supposed to be more than 80 Hertz. Let's review this least resonant frequency. The first natural frequency is now 129.04 Hertz, which is more than 80. Again, this condition is also being satisfied. Now, from this, where static performance and frequency performance of what we initially designed is satisfying, now we want to have an optimization. Therefore, we go again for evaluate, create a design study, where this time, if you have the professional license, the optimization tick mark should be on. The difference we get here, we have the goals section added and working. Same procedure we have to follow. Simply we bringing our variables, we bringing our constraints, and now we have to bring our goal as well. Let's review the study I've created here in a variable view. The first stage is simply I'm bringing on my list of variables: back plate height, feet width, and back plate. I said it should be varied from in a range of 50 to 150 millimeter. For the other one is 100 to 250, and for the third one is 150 and 375 millimeter. Then I have created my sensor. If we simply review them, first is the stress sensor on the whole model, maximum value. Next is my displacement. Edit the sensor, and you can see it is displacement value over the whole model, maximum one, resultant. Next was the other displacement. Here, where this time I've selected that edge, and I would like to trace the stress values here. And then after finding all the constraints is where we defining our goal. Goal is simply could be defined as a sensor as well. So you're creating a new sensor, but this time instead of simulation data, you're selecting mass properties on the whole model, and you're clicking OK. If you do that, then here is what you have. Right now, you have a mass sensor of press, and clicking OK. This is the other sensor we put here. Also, we have defined a frequency sensor here for the hertz, maximum over the model, and at the specified mode shape, which is the first natural mode. All right, now we have the list of sensor. We put our constraint on the sensors. As you can see, stress 1 should be less than 100 Newton, which the initial data is coming from press static. The static case we created here. Displacement 1 should be less than 1 millimeter, press static study. Frequency should be between 80 Hertz and 150 Hertz, where the result is coming from press frequency. Displacement 2, which is on the edge, should be less than 0.5 millimeter, and it's coming from press static study. The additional parameter we have to define compared to the design exploration is the goal, where we're saying we would like to select the mass sensor to be minimized. Okay, table view simply showing us what we have created, and result view will showing us what is being achieved. Click on run, then you have this result uploaded. Here it is. The difference, as you can see here, the current status the initial status, and the optimal one. Look, and we have review. First of all, it will showing us the back high, the fit high, and back plate high on the optimized model. Stress value is 95. Displacement value is 0.5 to 6 millimeter. Reviewing further down, frequency first natural is 80. Displacement on the edge is 0.27, and the mass is 59948 grams compared to what it was, 73953. In any aspect, you can review your result. It was 100 millimeter initially, where in the optimized model it is 67. It was again here 375, where in this case we get 199.45. And the stress value is more, displacement value is more, frequency is less, but we get a lot of mass reduction. That is the optimal model. However, we have set of iterations being listed here as well, where you can see there are some of them with the red marker where there is something wrong with that iteration. For instance, if you look at iteration number 3, then you can review that. The stress value is 124, means simply it's failed one of our conditions. Iteration 4 has the same problem. Iteration 5 is okay, but you simply increasing your mass, 75933 compared to 73953 grams. It is more safe, but you haven't saved anything here. And further review simply showing us anything on all the scenarios software considered and resolved for us. However, at the end, this is the optimal value. You can review the other iteration just by selecting them and look how the model is changing. Also, it is available for your optimal value to see your sensor in detail. For example, one misses stress as you defined, displacement, frequency, and displacement on the line. Also, you are able to get the graph view for mass, how it is being changed over the back plate in millimeter. Also, we can have frequency while the back plate is simply changed. Again, that could be achievable about define local graph. X-axis could be any of these parameters if you like. Objective or constraints, mass, displacement, frequency, and whatever. Optimal, initial, any iteration. So simply you defining your graph, and now you can simply review the whole idea as it's changing through the range of the variation, but software is simply showing us the optimal value, as you can see here. All right, so that is bringing our case to the conclusion. And let me first ask if there is any question and everything is clear to you, or you would like to have any question before I keep continuing and terminate the session. Any question, please? So waiting for any question if it's coming through. All right, seems not to be. Question regarding the global contacts. So the global contacts is, I have no idea if your question is regarding how we define this. Usually when you bring your model as an assembly, then simply the global contact is automatically being assigned there. However, you can modify this and make, let's say, no penetration, a low penetration, or bounded locally as well if you have the assembly. But this is separated case and it's not related to our design study. There is nothing specific in our design study actually let's say facilitated or similar options. Are there any welds? That is again could be defined as a set of constraints. So any let's say form you want to create your static study with considering pins, springs, weld, any contacts, whatever it is, doesn't really matter. You can simply put in there, solve your static study, then when it's been solved, then you will consider a design study after a while. So yes, it could be define anything as you have created in your static study here. You can go to your connection and apply anything, spring, pin, bolt, weld, anything, and then simply solve the model, then go for optimization. Okay. So before we finishing this, I would like to reintroduce a very quick fact. Here is the slide. This is what I'm usually reviewing for everybody. That's our product has initial licensing of SolidWorks Premium, which you will have static and motion simulation case active. If you like to have more option by going through fatigue, thermal, frequency, optimization, which is the topic for today, drop tests, submodeling, pressure vessel, buckling, and event-based motion, you have to upgrade your software to SolidWorks Simulation Professional. And also at the end, if you need some nonlinear static analysis or linear dynamic or composite or nonlinear dynamic, the next upgrade would be simulation, SolidWorks Simulation Premium. All right, I would like to thank everybody for listening. Reminder of 20th of September, we have steady state transient thermal analysis in SolidWorks and the seminar on 26th. Again, if you're interested for, let's say, to attend, please send me an email, and this is my email address. Anytime you can forward your question at the end, and I can answer it offline for you. I can see there are one more question coming in, but yeah, you can send it forward it to me on an offline base, and I will consider this for you. Again, thank you everybody, and wish you all the best, and see you hopefully on next week.